Hello, I'm Cindy Croson. I'm a professor of biostatistics and medicine at Mayo Clinic. In the first module, we discussed what survival analysis is and when to use it. We discussed types of censoring and how to compute survival probabilities using the Kaplan-Meier method. Picking up where we left off, in this module, we will discuss how to compare two Kaplan-Meier curves, and we will discuss Cox proportional hazards models, which can be used for more complicated comparisons. Now we start with two Kaplan-Meier plots for two different groups of patients. These might be men and women, or patients with surgeon A compared to surgeon B. When you have two groups, and you want to compare them, the simplest method is to compare the two Kaplan-Meier curves using a log rank test. This will give you a p-value, but no measure of effect size. If you want to get a measure of the effect size, or you want to adjust for something that may be different between the two groups, like age and sex, then you need to use a Cox model. The Cox model is the most commonly used model for time to event data. The Cox model provides a relative risk measure called the hazard ratio, which is the ratio of two hazards. So the hazard ratio is the hazard for group 2 divided by the hazard for group 1. If it's bigger than 1, this means the risk of an event is higher in group 2 than in group 1. If it's less than 1, it means the risk of an event is lower in group 2 than in group 1. And if it's equal to 1, this means the risk of the event is not different between the two groups. But what is a hazard? Here are several survival curves, and I just used the U.S. white population life tables for persons alive at age 50 in the year 1940 and also in the year 2000. The survival is better in 2000 than it was in 1940 for both sexes. Males consistently have poorer survival than females. These curves are smooth and not bumpy because they are based on the whole population and have been smoothed when converted to life tables. The hazard is the instantaneous rate of change of these curves. So we can see by these lines that show the slope of the curve at two different points that the slope is steeper at older ages than it is at younger ages. So the death rate or the hazard is increasing as age increases. These are the hazard rates, or the yearly death rates per 100 subjects. So you can see they are increasing with age, and they are increasing quite a bit at older ages, kind of exponentially as people age. Interestingly, if we plot these on a log scale, they are straight lines, which demonstrates that the increases follow an exponential distribution. This pattern has been shown in many diseases. This is one of the reasons the Cox model is computed on a log scale. The other major reason is that the hazard cannot go below 0 when you're on a log scale. Here's the formula for the Cox model. It includes a hazard rate that is a function of time and does not depend on the covariates. Then the second part of the formula involves the x's, which are the covariates of interest, and the betas, which are the coefficients. But that part of the formula doesn't depend on time. This means the hazard ratio does not depend on time. The hazard ratio is obtained by exponentiating the coefficient. This hazard ratio corresponds to a 1-unit change in the covariate x. So for a binary yes-no variable, we typically code that as 0 for no and 1 for yes, so a 1-unit change is the difference between the presence and absence of the covariate. For a continuous variable like age, the hazard ratio is for a 1-unit change. Sometimes a 1-unit change is not meaningful, so you may want to transform the continuous variable to get the hazard ratio for a different unit change, like 10 years of age. How the Cox model works is it makes a calculation at each event time, so it compares the covariates of the person with an event to all the other people under observation at the time of the event. These calculations are combined into a partial likelihood, which is maximized to estimate the coefficients. Time-dependent covariates can be used to represent data that change over time during follow-up. If it's just a simple unexposed exposed, then the patient will be unexposed prior to development of the covariate, in this example, the diagnosis of diabetes, and then exposed afterwards. In this example, the lines are white for people who don't have diabetes or prior to developing it, and they are blue on this figure beginning at the diagnosis of diabetes and thereafter. So some of them are already blue at time 0 because they have diabetes before study inclusion, and others are white the whole time because they never developed diabetes. At each Cox model calculation, only the values of the covariates at the time point are used. For continuous time-dependent covariates like blood pressure, over time, you just change the value whenever there is a new measurement. Instead of changing from no to yes, you change the numeric value for the next interval of time. What are the assumptions of the Cox model? Whenever a statistical model is fit, it's important to assess the model assumptions. Important assumptions for a Cox model include non-informative censoring, as well as proportional hazards, leverage, functional form, and additivity. The proportional hazards assumption means that the hazard ratio or relative effect of a risk factor of interest is constant over time. For example, if males have a 1.5-fold increased risk of early post-surgical complications compared to females, they also have a 1.5-fold increased risk of late post-surgical complications compared to females. This assumption is often violated in surgical data. When post-surgical Kaplan-Meier curves cross for males and females, the proportional hazards assumption is violated. This figure demonstrates a violation of the proportional hazards assumption. The coefficient for the biomarker changes over time. It is less than the average coefficient for the first 100 days and then increases to more than the average coefficient after 100 days. After 100 days, the coefficient is not significantly different from 0, which demonstrates a common phenomenon that the ability of a biomarker to predict an outcome may dwindle over time. In addition to the assumption of proportional hazards, Cox models do not differ from other regression models in that they require diagnostic assessments of influential or high leverage points, linearity of any continuous covariates, and potential interactions between covariates. High leverage observations are patients who have extreme covariate values that have a large influence on the estimated coefficient in the model. An example is a patient who experienced the event very early or very late relative to other patients in the cohort. This figure shows influential points in the upper left and bottom right corner of the figure. These points at the youngest and oldest ages correspond to changes in the coefficient for age of greater than 0.4 increase and decrease, respectively. Consideration of nonlinear effects is particularly important because factors such as body mass index may have nonlinear J or U-shaped effects on an outcome of interest. And this may be missed when only linear terms are considered. This figure demonstrates a potential nonlinear relationship where the coefficient for age is less than 0 prior to age 50 years, becomes greater than 0 for ages 50 to 70 years, and then downturns again after age 70 years. A spline is used to examine this possible nonlinear effect. Splines are available in many software packages, and other methods to check for nonlinear effects are also available. There are a few other common pitfalls in survival analysis. The two most notable ones are competing risks and immortal time bias. Competing risks occur when something happens that makes it impossible for the event of interest to occur. For example, for an event that is not death, death is often a competing risk. This is addressed in another video in this series. Immortal time bias involves using future information as if it were known at study entry. To avoid immortal time bias, covariates used to divide patients into groups for Kaplan-Meier analyses or used as baseline covariates in Cox models must be known at baseline or study entry. It is incorrect to use future knowledge, such as hospital days or the presence of a staged bilateral arthroplasty, as if they were known at baseline. These two issues are very common in the orthopedics literature, and both competing risks and immortal time bias are explained in more detail in other videos in this series. In conclusion, time to event data in orthopedics requires survival analysis methods, and survival analysis should be used more often in orthopedic research. These data involve specific nuances that need to be addressed, which may be overlooked by researchers with limited knowledge of survival methods. It is important to involve a biostatistician as part of your research team prior to data collection. The most common errors encountered in analyzing such data include using methods designed for binary outcomes, failing to check proportional hazards, ignoring competing risks, and introducing immortal time bias by using future information. Researchers should be careful to avoid these pitfalls, and reviewers should be on the lookout for these issues when reviewing manuscripts for publication.